Welcome students, lesson number 11. Today I will be talking on errors in GPS observables. In the last class we have seen that GPS observable consists of code pseudo range and carrier phase observables, and these observables are fraught with errors. In today's class we will discuss on what are the defined sources of errors and how those errors has to be taken into consideration. Now the lesson will be discussed under the following heads, that what are the errors, different types of errors, then the summary and review questions and further reading. GPS observables are fraught with mistakes as well as errors. Mistakes means the error which is done inadvertently without knowing it, and errors are coming automatically. So the mistakes actually we can avoid by making conscious effort. Now these mistakes and errors arises out of defined sources. So we need to know what are the different types of source or different sources from which these errors are coming, and what is the nature of the error. Depending upon the nature of the error we may take care for further processing. Now depending on the nature of errors, actually errors are divided into three broad categories, that is gross error or mistakes, and systematic error and random error. Now as I told you that inadvertent mistakes, that means some errors are coming due to undesirable field condition, confusion and carelessness of the observer. So we should avoid these conditions to reduce or to avoid gross errors, and these gross errors will be always there with the observations. So we need to identify those errors, and then subsequently we need to remove those errors, we need to reduce that error, we need to correct those errors, and this is done during the pre-processing operation. Now apart from that gross error, so gross error, so this is the inadvertent mistakes, then systematic error. So from the name itself it can understand that the errors which are related to the system, that means the GPS system. Here in our case for the user it is the whole of GPS satellite segment, then the signal it is coming through the atmosphere and the GPS receiver. Now these systematic errors actually follow certain physical laws which we should look into, and we can model those errors and then we can remove it. So systematic errors are errors which can be modeled and removed, and these errors actually vary from observation to observation. For each observation the same type of error may be different. And the third one is called random error. From the name itself we can understand that random errors are very random in nature, that means no one can predict how these errors will come and what will be the nature of this error. So again random error can be should be avoided and can be minimized through some due precaution as well as through statistical analysis. So now we should go for the gross error. Now the sources of gross error is primarily the, as I told you, that some unforeseen condition in the field, or if the signal that is coming from satellite to receiver, it may get interrupted or interfered due to some sudden phenomena, or unforeseen phenomena, or sometimes the person who is carrying out the GPS surveying, they may not be efficient or competent enough to carrying out the GPS surveying. So, they may do some mistakes, like they may not be able to maintain the receiver in perfectly centered or perfectly leveled, or there may be some mistakes about the antenna, its nature, and so many other things. So, there are those errors due to negligence or incompetence of the observers, or due to unforeseen reasons that may occur in the field. This cross error may arise in the GPS observables. So, after taking the observations, we should need to test the quality of the observables or the content of the observables, and we need to identify, we should identify whether our observables are associated with gross errors or not. Now, some of the steps which we can take before taking any observation, like whenever we take the, suppose this is the terrain and maybe some buildings are there here or some trees are there. So, we should take the cutoff angle in such a way that it does not, that means signals from GPS, suppose GPS satellite is somewhere here. So, we should not allow it to come here by making the cutoff angle more than the obstruction. So, by taking cutoff angle properly, by avoiding location where there may be some undesirable reflection from around, like if we say this is the area where we like to go for GPS observation, this is the station, we should avoid any water bodies around, because these water bodies acts as a reflecting surface. So, it provides some undesirable signals, so that will affect the GPS observation, or the observables will be associated with the gross errors. Then the receiver should be properly centered, that means just above the point from which it is, for which we want to get the observation location, or it should be leveled properly. We should make use of the proper instrument. So, all these things will help to avoid the amount or nature of gross error. Whenever we get the GPS observable, the simplest way to identify the gross error is to go for some test called statistical test. So, suppose we have n data, so we should find out the mean and standard deviation, and we should see whether all the data is within mu plus minus 3 sigma. So, this is the generally this is a very simple way to do. That means, if the observations are within the mu plus minus 3 sigma, then we can say that the errors, that the observables are free from gross error. This is a very simple test, and there may be so many other good tests, better tests, statistical analysis, which will provide us an indication about the presence or absence of gross errors. Next type of errors is the systematic error. Now, systematic error, actually what we do see, that this is the GPS from satellite vehicles, and signal is coming, and this is the receiver where the signal is being received, and we can say that this is the atmosphere, troposphere, an ionosphere. Now when the signal is coming from satellite vehicle to receiver, it will transmit through the atmosphere. Now there may be error associated with the satellite vehicle or orbit. There may, that is called space segment error, systematic error, or the signal that is coming from satellite vehicle to receiver, this signal may not behave or propagate the way it is expected to do because of the presence of ionosphere and troposphere. Its velocity of propagation as well as direction of propagation will change. As a result, there will be some delay in coming the signal to the receiver, and that will cause error, and that is called atmospheric error. So there will be some atmospheric error. First one is space segment error, number 2 atmospheric error, number 3 there the receiver may not function the way which it is expected to do or work. So receiver error. Apart from that, there may be some other error. So other error. So under these 4 heads the systematic error may be explained. Now the first is your space segment error. It has 2 types, one associated with the satellite vehicles and other with the orbit. Now again in the satellite vehicle there may be 2 types of error, one due to satellite clock error and other due to satellite antenna phase error. Now as I told you that the satellite vehicle makes use of atomic clock, and these functions on the basis of GPS time system, GPS time system. Now the clocks that is being available in the satellite vehicles, they may not perfectly synchronized with the GPS time system. So there will be error in satellite clock, and that error of satellite clock we do get the information that is modeled through some functional relation, and the parameter of those function are available in the GPS navigational data. So model coefficients are available in navigational masses, and these coefficients will help us to compute the error in satellite vehicle clock. Then there is a error in satellite antenna offset error, because satellite antenna, the antenna phase center of the satellite antenna will be defined from the center of mass of the satellite. So that distance will make an error in the satellite ranging value, that means in the GPS observable, and these values we can get from this internet site. And the third error, that is ephemeris error, which is the orbital error, that means the satellites are planned to move around the earth at certain orbit, but it is not possible for satellite to move as per the desired orbit. There will be some variation, and that variations are known as ephemeris error. So ephemeris error may be minimized or avoided by making use of precise ephemerides. So, for long baseline or for very accurate GPS point positioning, we should go for very precise ephemerides. Then the signal as it comes out from the satellite vehicle will transmit through the atmosphere and reach to the receiver, but while it will come, it will interact with the ionosphere as well as with the troposphere. Now in case of ionosphere, that means ions are there. So, and electromagnetic signal is also electromagnetic in nature. So, they will be much influenced, or there will be a lots of perturbation in the signal propagation through ionosphere depending upon the intensity of ions available, and the error associated with that is called ionospheric error, and that is electrical in nature, whereas the troposphere contains the many physical particles like water bubbles, then other particles, and physically that will hinder or obstruct the transmission of GPS signal, as well as which the velocity of propagation as well as direction of propagation will change, which will make this signal propagation time delayed. So, this will make the errors in GPS observable, and these errors can be actually, for atmospheric error we generally go for modeling and then we reduce the errors through modeling. Now, the third type of error that is arise around the GPS receiver, as I told you that GPS receiver will be having an antenna, and always there is a problem with the antenna phase center, because the defined components of the GPS signal will have different location of antenna phase centers. So, different types of observable will have different errors. So, the best way to minimize the antenna offset error is to make use of the same type of antenna for different types of different receiver used in a project. Receiver hardware error, that means that receiver is a electronic instrument, so it may not function the way it has been designed due to defined field condition, temperature, pressure, humidity and something like that. So, if it does not work the way it is being designed, then there will be some error, that is called receiver hardware error. So, to minimize receiver hardware error, we need to take the receiver which is very robust in nature, and we should make use of field condition for which it is being designed. And the most important and most dangerous or most significant error that is associated with this GPS system is the receiver clock error. Already we had discussed in our class of GPS positioning that the clock in the satellite vehicle is the atomic clock, which is having the precision of the order of 10 to the power minus 12 second, 10 to the power minus 13 second, 10 to the power minus 11 second, whereas the clock we use in GPS receiver is of quartz nature, having the precision of the order of 10 to the power minus 6 seconds. So, there is a error called synchronization error between the satellite vehicle and the receiver, and that makes a very large error in GPS observable. That is the reason why the GPS observable is not the range but the pseudo range, and it is being taken as an independent error and is being used to find during GPS processing. Under the other types of error, there are two errors which are very prominent, which is called multi path error. What is multi path error? So sometimes if we set up the instrument near some building or some tree, signals from GPS will not only come directly to the receiver, but also it will get reflected from adjoining building or trees. This phenomena is known as multipath. Now due to multipath, because it is coming from the same GPS satellite, and they are leaving the satellite at the same instant of time, but it will reach at different times because of the different path it took, as a result of which the signal will be corrupted, undesirable errors will come. So this type of error is known as multipath error, and this type of error is more prominent in CA code observation. And the step for reduction of multipath is that we should avoid a place where there are some objects around and from which the signal may get reflected to come to the receiver, or we must avoid areas like in a crowded building, trees, or some adjoining water bodies. Water bodies also reflect and acts as a reflector. And another way to take care, because otherwise it may not be possible to choose that type of ground or that type of station. So nowadays there are some specific type of antenna available called choke ring antenna. This type of antenna actually rejects multipath. The idea behind multipath is that it gets polarized, and that polarity of the signal, direct signal and the multipath signal is different. So whenever it receives signals of different polarity, they rejects, and that is the concept of multipath resistant antenna. And that type of antenna if we use, then we will be able to minimize the multipath error. The next type of error, other error, is that cycle slip. Cycle slip errors occur suddenly. Suppose the signals are coming from GPS satellite vehicle, and in between some obstruction may come. Suppose there is an aeroplane. So for some time this aeroplane will obstruct the signal, and once it will leave, again the signal will be coming to this, as a result of which that integer ambiguity will be restarted, a new integer ambiguity will come. So if we plot phase observable, number of cycles by time, you will see, you will find it is increasing. Suddenly it may decrease and then again it will increase. So that means corresponding to this time there is a slip of cycle or discontinuity in observation. sometimes it may be like this, sometimes it may be like this, it may increase like that. So, corresponding to that time we can say that there was a disturbance in signal reception, and so there is a sudden increase or sudden decrease in number of cycles in the GPS phase observable. This phenomena is known as cycle slip. Now during GPS data preprocessing, in the we can identify and remove the observation corresponding to this time. The different types of systematic error, the most dangerous error is that receiver clock error. Receiver clock error is the most dangerous. So, this error is being considered independently. Receiver clock error is the most significant, and it is so high that we do take this error as an independent unknown and we do resolve it before we go for any GPS point positioning. Among the other errors, it is the ionospheric error, which is most prominent and to be avoided and can be avoided by modeling. Then it is the multipath error, and ionospheric error is of different nature from code and carrier phase. Then multipath error is the dangerous most, third most dangerous. So, this is the sequence of its error. And the third kind or the last kind of error that the GPS observable may have, that is called random error. Now from the name itself we can understand that the errors which does not follow any rule, the errors for which the observer has no control, those errors are random errors, and random errors can be avoided or minimized by proper planning and execution of GPS surveying. Also we do take care of random survey by statistical analysis. Through statistical analysis, what we do, the errors, random errors associated is distributed to different parameters, so that each of the parameters, computed parameters, have some error which is very insignificant. Thus we can say that the pseudo range, the GPS observable pseudo range of any range from satellite I to receiver R is equal to geometric range plus the error due to receiver clock error C into del TR, C into del TI, that is the satellite clock error, ionospheric error and tropospheric error, ionospheric error plus tropospheric error, receiver hardware error, then your satellite vehicle, then your multipath error and random error. So this expression provides us, that means the pseudo range observable which we get from GPS observation, we get this number, but this number will consist of all these components. Similarly, if we say about this is the carrier phase pseudo range, that means carrier phase observable multiplied by the wavelength, that is the carrier phase observable. So, we can again, this is geometric range and this is the integer ambiguity. So, number of integer ambiguity multiplied by the wavelength will give you the error due to integer ambiguity, that is the total number of cycles in the first epoch of observation. Then you will have C into del T R, C into del T I. Now, here you can see the ionospheric error is opposite in nature, that is here it is plus but here it is minus. So, tropospheric error plus dTr dTi dTr. Now, one thing you should remember, that though I had written the same symbol here, it is okay, geometric distance is same, this is that satellite clock error is same as this, but these values I should rather write dash, because the amount of other errors will be defined from your in the code and carrier, these errors will be defined. So, we should better write some other symbol like dash. The amount of other errors are different for code and carrier. So, as it is written here, code errors associated with code and phase also differ, and also between the type of codes as well as on the type of carrier. So, with this I like to conclude this class. Now, let me summarize about this class, that GPS observables are fraught with errors. Errors are of different types depending upon the sources from which it is being aroused, and we do divide it into three types: gross error, systematic error and random error. Gross error are the errors or mistakes which we can avoid by taking due precaution. Systematic error are always there, so we have to make use of some model or methods to minimize or to remove this, and random errors are the errors which can be avoided through meticulous planning and execution of surveying and as well as statistical analysis. And with this, let me conclude this class. Some review questions, and for your further reading, this is the book, and in the next class I will like to take GPS data preprocessing, in which we will see some very simple methods through which we can minimize the errors that is associated with GPS observable. Thank you.